You don't have to write something down with a pencil. You know why you can't write with a broken pencil? It's pointless. Sorry, I'll stop there. In nature, you don't have a vacuum. So nature, it's an old vacuum joke. Nature abhors a vacuum. So what are we going to cover here today? Well, so we'll talk about vacuum characteristics and why are we talking about vacuum at all? Fundamentals of vacuum technology. So there are a few maybe slightly boring, but something that you should know about different kinetic theory of gases, conductance. We'll talk about the problems you have with a vacuum. And then the meat of the course is here. We'll certainly be spending some time with safety, but we want to show you the pumps, the pressure measurement systems, and the hardware. And then we'll talk about troubleshooting. This is NC State. You're supposed to make a sound. So, why do we need this? Well, so I worked here, I'm now retired, I worked here 20 years in the analytical instrumentation facility. So if you have a piece of instrumentation that uses ions or electrons, they don't go too far in air, so you're going to need a vacuum. And a number of you mentioned that you're working with CVD or something like that, and in that case, your process needs a vacuum. It may need a very good vacuum. And you have issues such as oxidation, gases in the chamber. So we'll try and touch on all of those. All right, so we have three characteristics here. One is you first turn on a roughing pump. We're going to show you some of those right here. And in that case, you're looking at air. So it's mostly nitrogen and oxygen. Now, as we go to a better vacuum, here the gases are what's in the original chamber. Now it's from the surface. This is what's called a viscous flow. The other is a molecular flow. And you understand those, they're quite different. And now your gases are water. Water is something we'll talk about a lot because if you have water in your system, it doesn't pump down very easily. Nitrogen, CO. Once you get to ultra-high vacuum, this may be a surprise. It's all hydrogen. So then it's all about your seals, how well you've made the connections. We'll see something similar to this several times. So on the x-axis, we have increasing pressure, ultra-high vacuum, high vacuum, rough vacuum. And you'll see different characteristics here. So vacuum cleaner, not a good vacuum. Incandescent bulb, vacuum tube. How many of you have never seen a vacuum tube? Okay, so imagine a computer made up with these instead of transistors to make it. All right, so there's your vacuum tube. Surface analysis chamber. I look downstairs and our XPS is right now in the low 10 to the minus 10 torr regime. That's about the same as the surface of the moon. Interplanetary space, well, maybe one of you want to go there. I don't think I'll make it. So your SEM chamber may be somewhere less than that. So this is a type of slide that we'll show several times showing pressure on the x-axis and characteristics of the pumps and the measurement systems. Ideal gas law. Hopefully you've all seen this. PV equals NKT. The thing to understand is that pressure and volume are inversely related. So if you've got a certain amount of gas and you decrease the volume, you're going to increase the pressure. Let's look at a couple of things that maybe you're not thinking about is how fast are those molecules moving around? At 20 degrees C, and I won't show derivations, there are lots of references, you can always look these up. At 20 degrees C, 472 meters per second. And I guarantee you that'll beat anybody at the Olympics trying to write in the time. And rate of arrival of molecules at a surface. I may not be thinking about this, but at 10 to the minus 6 torr, if every molecule that hits sticks in 2 seconds, silicon's like 10 to the 15 atoms per centimeter squared. That's typical for a lot of materials. In 2 seconds, you would have a monolayer on the surface. So if you're doing CVD or something like that, you can't do it at 10 to the minus 6. You're going to have to be much lower in pressure than that, 10 to the minus 9, 10 to the minus 10, something like that. So that's something interesting to think about. And we'll get to this with the water shortly. Another concept which is very important to understand, mean free path. How far does the molecule go before it runs into something else? And really simple equation here. But here we're talking about atmospheric pressure. This will be this dynamic flow. And here we're going to have this low pressure here. So let's take your vacuum cleaner. And we actually put a pressure measurement on your vacuum cleaner, see what the vacuum went to. And numbers you should have in your head are 760 torr is atmospheric pressure. We went down to 630 torr, which is good enough to pick up your dirt. But your mean free path is 79 nanometers. So we can't use it. Now let's look at something really big. This is the largest one in the world. NASA uses it. It's in Ohio. I don't know if they give tours, but you can go and look at it. And you've got some module in here. 2 times 10 to the minus 6 torr, but you're pumping out the building. So here's what that other one, which is interactive, and you can play with this yourself. So if you have a lot of gas in the system at 760 torr, your mean free path is only 40 nanometers. Your collisions are between the molecules. That's what exerts the pressure. If you have very little gas in the chamber, your collisions are with the walls. What does this mean? It's something we'll emphasize in a video showing before long. Once you remove just down to like 10 to the minus 3, not even that, you've taken all of the force away from it. Throughput and conductance. So throughput is how much gas is flowing through a vacuum system. And the throughput is the same across all planes in the system. So here we've got a vacuum chamber. As you neck this down, your conductance has to increase. Conductance is the flow across the plane. When you're looking at your system and you're deciding, hey, do I need a bigger pump, whatever I'm going to use as a rating, look for liters per second. That's the term you normally find. It'll be maybe a 300 liters per second turbo pump or a swirl pump, 120 liters per second, something like that. That's the term to look for. So let's take some examples of conductance. Here we've got a large throat, easy to pump. Your vacuum. Hey, we need spell checker on this. And then this one's narrower. The vacuum's not as good. This one's even narrower. The vacuum's poor. This one is convoluted, and the vacuum is worse. So if you're putting your system together, you want to look for short runs from your forepump to your rest of your chambers. If you've done electronics and if you looked at resistors in series or parallel, something similar. Conductance for these three is greater than the largest tube. In series, it's poor. Once again, you don't want to have a really tiny little tube to pump out a big chamber. What are your issues with getting a good vacuum? Gas sources, absorption, and water. What are your sources? Well, there are all kinds. You can have something desorbing from a surface. You can have a leak in your chamber. You can have a virtual leak. Virtual leak simply means I've got something and it's so tight, like a screw thread, the gas can't easily get out, so it keeps coming out at a very slow rate. Outgassing from the sample. Permeation, that means your seals will leak, especially hydrogen. Backstreaming from your pump, so if you've got an oil pump, you can get streaming back. And initial or vent gas. Physical absorption occurs when the gases are close to the liquid state. So here we're mentioning the sticking coefficient of the gas to the surface. It's not always 1. It can be a lot less than that. So remember I said 10 to the minus 6 torr, 2 seconds you're going to cover the surface. What's our real problem? Water. Yes, we do live in North Carolina. It's usually humid. We haven't had as much rain. But if you open your chamber to air, all that water gets in. What's the problem with water? Its sticking coefficient is essentially 1. So this means I've opened the chamber, I've got the water in there, and every time the water molecule hits somewhere, it sticks. This is why you see people baking systems, and you bake it above the boiling temperature, above 100 C, and then you can pump it out more quickly. So that's something we'll dwell on when we talk about other issues. Chemisorption, change from a gas to a solid. And some of the pumps you're going to see, well, we'll show them a little bit later, like the ion pump, use titanium as a surface, and it's a fresh titanium surface. It's very reactive. So the gas molecule hits it and is trapped by this chemical surface. Safety. Pressure on this chamber can be enormous, and we'll show you some calculations and examples of that. So if you've got a flexible bellows and it's not supportive, you start pumping, it can move it. I've seen a mass spectrometer nearly ruined that way. And if you've got these glass surfaces, then like a viewport, then that's something that can be easily broken. Not easily, but can be broken. An explosion, you normally must have a relief valve for certain high pressure systems. Your gas cylinders, and we'll be doing some demonstration with that, and your cryopumps, which are pressurized. So let's look at this little tanker car video. And won't go through all the calculations, but if we pull a vacuum on this, it's a very weak vacuum. We're only going to 0.52 psi. We're going to put 62 tons of force on it. Toby, how can I... So they're hooking up a pumper to an empty gas cylinder. This is a tanker car you see on the road, and I think I looked it up. I think the steel on it's like half an inch thick, something like that. So there's their connection. I think I saw them putting duct tape on them. 27 minus 27 psi. What do you think? So don't build your vacuum system out of weak stuff. All right, so trick question. Which one has to be stronger? 10 to the minus 3 torr or 10 to the minus 11 torr? Any guesses? Once you've got to 10 to the minus 3 torr, there's essentially no difference between that and 10 to the minus 11 that you can physically measure. So that tanker car, they only went down 0.52 psi. We're not even in the low torr range. We're not 10 to the minus 1, you know. So, so in terms of checking out a system, if you want to see if it's straight, if it's going to survive, you just need a forepump to be able to do that. Many of the analytical instruments that we have are around 2 feet by 2 feet, let's say, in size. 25 tons. So if you see them and you see all the stainless steel and torque-rated bolts, that's why. I can see you guys trying to figure out how I can get to a railroad and put a pumper on it and pump down one of those and try it myself. Your car is about 2 tons, so that's about 12 cars on top of your system. All right, safety. Didn't happen to me, but it happened to a group. They had a oil pump like this. They pushed the wrong button and they were pumping out an oxygen cylinder. That started the oil on fire. So they have multiple problems. So it's something to react with. And I know if you're doing CVD or something like that, you may be working with some very nasty gases. And we'll talk about that and talk about ways that people handle them. These sputter ion pumps and cold cathode gauges, they have high voltages on them all the time. May not kill you, but you won't like it. So you have to remember that high voltages may be present. Hazardous gases, that's where you have to have some way to vent them or have a scrubber or something like that to contain them. Hazardous solids, those titanium films, are very reactive. And so if you just open a system, then you may have a problem with that if you touch it. Record keeping is very useful. So you should have a logbook. It can be on your computer, that's fine. This particular one is from a focused ion beam, and at this point, the gauge went bad. In your record should be how long it normally takes you to pump down your system. When did I last change the oil? Did I ever change the oil? You know, things that are useful. Gee, what are the spare parts that I need to fix this the next time so I don't have to look for it? But either here or on your computer, whichever. But you really need to do that. Remember, not with a broken pencil. Typical system has some forepump and probably a turbo pump, some gauge to check the pressure in your forepump. And here's your sample introduction chamber. And then we're assuming that you want to put something in here and then put it into your working chamber. And there you may have an ion pump or titanium sublimator. So those are some of the typical pumps you'll see. In the analytical world, your TEM. How many of you use one of the TEMs here? No TEM users. Okay, they've used TEM. Only 15 milliliters. The XPS, 5 liters. So you can pump this down quickly. That you have to spend hours pumping down. So it depends on how big that chamber is, how much water you put into it. This is a typical vacuum synoptic is what it's called. This symbol is a pump, that's a valve, that's a gauge. And many of these are interactive. So if you click on this, you're opening the valve, something like that. If you don't have one, or it's your home-built system, you should have your own drawing of what it is. And the system that we have right over there that we're going to play with just your PowerPoint, you can easily put in whatever you have there. I think that's very useful because, number one, you may not be the only person using it. You may want to not have to explain it all the time. And in an emergency or just safety reasons, you can quickly figure out what to do. And we'll go to these, you'll get to touch all these and see. So here's your ion pump. You've got some cold cathode gauges, a leak valve, a gate valve, turbo pump, and there's a forepump sitting next to it. All right, so much for the boring part. Now we get to play with everything. All right, so How many pumps are there? Well, there are 4 pumps, and you're going to see these. This is a regular oil-driven pump, and you also have diaphragm and scroll pumps, diffusion pumps, turbo pumps, ion pumps, my favorite pump, ion pumps, titanium sublimators, cryogenic pumps. They're all used. The diffusion pumps less so than perhaps they were before. So now we're going to start to look at these individually. And here's that diagram I mentioned. We have pressure increasing on the x-axis. Here's your ion pump, cryo pump, turbo pump, diffusion pump, scroll pump, diaphragm pump. One pump does not cover your whole range. So if you're going to go from atmospheric pressure to 10 to the minus 9, you have to have something that pumps something like a turbo pump or diffusion pump or cryo pump all down to a certain level before you turn them on. And if that pump fails, the forepump, well, let's say your turbo pump might be $25,000. So if you ignore the fact that the forepump is not working, you will burn up your turbo pump. All right, so here's the rotary vane forepump. And if you look at this, here's gas coming in, and this is eccentric. Are we ready for the other camera to use that? And do you see it sweeping it out here? So here's your normal vacuum systems. A lot of them are heavy. They're also expensive, so don't drop them. Okay. So here's your motor. Here's this. You see this? And you're going to get a chance to touch this in a little bit. See this little piece here? Fits in here. The pumping volume is here. So you got this big pump and you only have a few 20 cc's or so space in here. This is made of really strong steel because it's got a lot of force on it. It gets hot. What's filling up the rest of this? Any guesses? It's oil. So there's a quart or more of oil in here, cooling this thing, which is going to be turning and becoming very hot. But your actual compression here is just this tiny area. There's another example here. You can see it's eccentric in its mounting. So you saw how small it is. You see it's eccentric and it just sweeps it around in there. Very important to understand that and just how small it is. Your motor, your oil with the actual pump area. Here's the connection to your system. You've got something here as an oil filter to try and prevent oil from backstreaming. And then you have something here to prevent the mist from getting into the room. There's a ballast control. Have you ever heard of that? Just say no. So the ballast control, if you're pumping nasty gases, will bleed air in at the same time. And I've gone to people who said, my pump's not working right, my pump's not working right. They're pumping just air and they've got the ballast open. So they're making the pump work double time. So look and see if your pump has a ballast on it and what the setting is and mess with it so you understand what it does. But that's how you help take care of nasty gases. If you've got MOCVD or something like that, you probably do. And you may bleed air into it, so it's not the pump oil or pump is not getting such nasty stuff in such high concentrations. These are pretty good. Maybe you change the oil once a year. What's the problem? Oil. And oils, many of these, after several years, it may leak, in which case you may be in for a new pump. So here's a vacuum tester. It's pretty easy to set up. You just need to hook. So you've got a problem. My system's taking an hour to pump down. It used to take 10 minutes. What's wrong? Is it the forepump? Is it a leak? Is it something else? So troubleshooting, you take this off, disconnect it, and you put something on here just to test the pump. And normally you can pump this down in just seconds to like 10 to the minus 2 or 10 to the minus 3. That was one forepump. There are two other types we're going to show you. One is a diaphragm pump. A couple little valves here and a little rubber thingy. If you've got a fish tank, for example, it'll be a little diaphragm pump. And that's all it is. It's a little piece of rubber. Just goes pretty quiet, works well. But I've seen people take a little membrane pump and try and pump out a chamber like this. And it would take them like 40 minutes, and they're killing this pump. They did not size the pump, or they ran out of money. Did not size the pump properly. So there's an example of one. And they're pretty small. This is the inside of one. We take everything apart when it dies so we can use it. And that's all it is. And there'll be usually two of these so it can have double the capability. Oh. After so many back and forths, the rubber tends to break. So it doesn't work anymore. You can get rebuild kits and take care of those. Depends on how often you use it, how much you're doing it. They suggest about 1 year. Actually, the one on the XPS has been running for probably 10 years and hasn't been changed. So here are the valves, and there are the connections from the valves. Now we'll go to the scroll pump. Scroll pump's really pretty neat. So here's your gas coming in. And it just gets squeezed, and then it goes out there. So this one moves, and this one doesn't. It's really a neat design. This has taken over as your forepump. Why? No oil. No oil. So if you look on the systems in our analytical facility, you won't see so many. Do we have any oil pumps at all? None. They're all scroll pumps. Okay. And if you buy a new analytical system from somebody, or you're buying an MOCVD system, I'm pretty sure you're not going to have an oil pump on it. So it's worth understanding this. What is interesting with it is the tip seal. So after a while, this is very precisely tightened so that the surfaces are just touching. And this one sets inside that one, but the tip seal is what goes in here. So if you can learn to replace this, you'll save yourself a lot of money. Here's a cutaway. This is all motor. And they're heavy. Remember, you have to paint your fingernails yellow if you're going to work on the tip seals. So here's your tip seal replacement. There it is replaced. You can see it inside of it. Normally the ones we have last around a year. Oil-free, reliable, has taken over as your roughing pump. Can be very noisy. Have to replace the tip seals. Now we'll talk about the diffusion pump. Oil, heat it up. The original ones were mercury. Don't do that. The oil is heated, comes out through little holes, and it comes out at supersonic speeds. So it may be 10 to the minus 8 or 9 torr here and 10 to the minus 3 torr here. there are cooling coils so that the surface is cool and the oil that hits it drops back down to the pump and is recycled. So you've got a pump here. It's an oil pump. And then your gas comes out here. Oil temperature, a couple hundred degrees. All right, here's a nice little video. Here's the oil coming up. And then you see it streaming out. Streaming out. So you've got this huge stream of oil. And now those are the cooling coils. Now you can see they'll zoom in here and you'll see the gas being pumped out there and the oil being collected down at the bottom. No moving parts, really neat idea. You need a cooled trap above this to prevent oil from getting in it. Changing the oil is difficult. They're not expensive, long-term reliability, unless your cooling water dies. And if it does, then you have something like this. Is that messy? Yes. What do you need to take it off? Something like trichloroethylene. You don't want to do that. Oh, so let's go back. So, and now, so here is your stack, and you can see the cooling coils here, your heaters here, you've got a thermocouple, and you've got various areas where the oil is streaming out. A couple of examples of that. These took a while to clean off. Turbo pump, my favorite pump. It's a jet engine. You can go up to 90,000 RPM, and I think that's what the XPS ones are running at. Your jet engine on your plane is about 10,000 RPM. It's much easier to show this video because that's actually a really good one that you found, Roberto. You actually have some of these moving and some of them not moving, and in a moment you'll see why. It can be very noisy. I'm wearing hearing aids. I worked with vacuum systems for 48 years, so it is a high frequency. Some of them are noisier, so something to remember. High-speed moving parts. But the latest ones, the cartridges that you use for lubrication, may only be replaced every 4 or 5 years. So if you want to start that one, this is a pretty good one. Gives you an idea. So here are your gas molecules. Here's one of them rotating, and this is a stator. So that's rotating, that's not. Here's your individual gas molecule. So these are, it's moving so fast, it's actually colliding and knocking the atoms. You see that? Cool, huh? Somebody spent a lot of time doing that. I think it was the Zoimans. So then you've got them all pumping down through there. You need a forepump to operate. You can't just turn it on. Are they expensive? Yes. So you do want to take care of them. And here's one that's exposed. Here's a small one. This was on a mass spectrometer. And this is exactly what goes inside of it. This doesn't have the stators in it. And the stators are going to look something like this. It's an aluminum base. These are high-tech materials. It's not just your normal aluminum. On the top of it, you'll have a splinter shield. So if you drop a screw in there, if something comes loose, it doesn't destroy it. And there's another one over here. You can actually kind of spin that one. So that takes us through on the time of flight sims You can see these are 60 liters per second. Remember I told you about that unit? That's something you're going to want to know. So we're going to the ion pump. Gas discharge caused by high voltage, magnetic field, helps take the electrons from this discharge and make them into helical paths. Why do you want to do that? To increase your chances of ionizing a gas. So you've got this assembly here, this anode. You've got a discharge. You have something that's ionized. They tend to be ionized positively. This titanium treated surface is negative, goes into there and gets captured. And if you look down inside, you'll be able to see this. You'll see one of these assemblies. So it actually traps the gas. Great, no moving parts, low pressures. Can't run it at high pressures. Can't turn it on in air, won't work. And at 10 to the minus 4, it's only going to last hundreds of hours. 10 to the minus 6, 50,000 hours. You're normally operating this 10 to the minus 8 or so. I've used them for more than 10 years, never had to do anything with them. Doesn't work as well for argon and helium. And they have little ones that can make it portable. Here's a big one. This is on a mass spectrometer. You need a crane for that. That's about 250 pounds. All right, titanium sublimator. How does this work? Look for the biggest cable on the instrument because you're going to put in like 50 amps. And you're going to heat up some titanium. And you're going to heat it up enough so that it actually sprays titanium out. That titanium helps trap all of the gas molecules. No moving parts. It's really quiet. Limited lifetime because the filaments will burn out. Normally have it with an ion pump. And the last pump is a cryogenic pump. How does that work? Cold. Use helium and you're down to less than 10 degrees Kelvin. So you have all of these chevrons here and your temperature drops, it goes up here, but you're down to 10 to 20 degrees Kelvin. You can trap a lot of material. If you go into a clean room, go to Intel or something like that, this is what you'll find. Lots and lots of these. Those are the cryopump systems. And you can see these chevrons, these surfaces, have a lot of surface area. Safety-wise, I think it's like 300 psi. They're really highly pressurized. So if you're taking off these hoses, whatever, you have to be careful. So rough vacuum, a 4-pump, high vacuum, 4-pump plus turbo pump, typically. Probably not going to use a diffusion pump. And then ion pump and titanium sublimator.